Here's another recurrence relation that I'm gonna solve by guessing. So we look at this using n equals 0. The first term is just gonna be the same as the 0th term. The next one is just going to be 2 times the first term, which was f0. The third one is just going to be 3 times the last one, which was 2f0. Next one's just going to be 4, 3, 2f0. And so you can see that the nth term is just going to be n factorial f0. So I think this is a pretty cool example just because you could think of this recurrence relation as just describing one property of this sequence, or this function, and we can see that the solution is just whatever functions have this property, and the solution is factorial functions multiplied by some arbitrary constant, which happens to be the start point of the sequence. So if we want to prove this using induction, you just call this statement P of n. We see here that the base case P of 1 is satisfied since 0 factorial is just 1, f of 1 is equal to f0. So now all we have to do is suppose that P of k is true, and then look at the k plus 1th term. So I'm just going to go straight to the k plus 1th term. According to the definition up here, this is just going to be k plus 1 times fk. And since we're assuming that p of k is true, that means that f of k is just going to be k factorial times f0. And k plus 1 times k factorial is just k plus 1 factorial. And so we have f of k plus 1 is equal to k plus 1 factorial f0, which is the same as my proposition here when n is equal to k plus 1. And so we see that p of k implies p of k plus 1, and so p of n must be true for all n. And so another thing I want to mention here, just because this is a pretty cool example, is that if you had a kind of functional equation, but it wasn't a discrete variable, like if you had f of x plus 1 is equal to x plus 1 times f of x, you couldn't use this method to solve it. You could maybe do the guessing part, and you could get your guess like this, but you couldn't use induction to solve it because this relies on taking 1 and then looking at the next integer, so it kind of relies on the domain being countable. So you could find functions that satisfy this just by guessing, and one of them would be that f of x could be the gamma function shifted back to where it should be, and actually any scalar multiple of that will work. So you could put an arbitrary constant, and this will also be a solution. But it does kind of make you wonder, are these the only solutions? Because there are other continuous functions besides the gamma function that go through all the factorials. And so that must mean that they have this property at least for integer values. So do they possibly have them for others? Is this does this functional equation here determine f of x? Does it say that this must be some multiple of the gamma function? So anyway, I just think this is a pretty cool example.